turn out different every time. You couldn't predict those things, and you would have to add they are random enough that they might not happen next time, or the so the asteroid sails by Earth and misses it by just a little bit, or your parents, somebody stubs their toe, they don't go to the dance, these kinds of things. Little tiny changes can have big influences, so there's nothing at all predictable about that right there. That's Homo sapiens. Never mind you. I just mean even upright, bipedal, big-brained, really dumb, shaped apes. That thing was so contingent on that and that, etc. that rewind it again, there's no way it's going to turn the same. All right, so now I want you to look at this picture because this is his whole argument here. He's not just saying that there's unexplored space up here. He's saying that there's no good reason that the space didn't get unexplored. Sorry, didn't get explored. It was just kind of happenstance. Now, I got to be careful here. Gould does not build his whole argument on randomness, unpredictability. He's not saying that. He would certainly agree with us that, well, it could be the reason this lineage thrived is because it was selected. It did better than the other ones. That's why it's there. He's not stupid. He knows that. He would agree. He would also say, but do you really think natural selection explained who was actually standing under the asteroid when it came down? The point is, those kinds of events can shape a lineage, and they're not predictable. And there's no good reason that this one didn't go up here. We don't have any right to conclude that this lineage here was fated for destruction because it wasn't smart enough, couldn't run fast enough, or whatever is your favorite adaptation. Okay, so let's think about a completely different way to look at the tree of life. And let me tell you about a phenomenon called evolutionary convergence. Here, evolutionary convergence is best explained by showing you examples, I think. The simple way to say it is evolutionary convergence is when two completely different lineages, perhaps separated by the circumference of the planet, arrive at what looks like the exact same solution to a problem, or the same morphology. This is my personal favorite. All those things look a lot like anteaters. At least some of them are anteaters. And they do not have an ant-eating common ancestor. They have some common ancestor, but this one arose there, and that one there, and that one there, and that one there, and as far as we can tell, we being people who actually know this stuff, they did not inherit that from common ancestor. They all developed it independently. That's a dramatic example of convergent evolution. The more famous one's yet to come. But I mean, so stop there. Do you see what's going on here? It's not a mystery. No one looks at that and says, whoa, what do you think? Adaptation, yeah, obviously. So it's not about proposing a mystery that requires an extraordinary explanation. That's not it. The point is, evolution actually tends to come back to the same spot over and over again. This is what Carmen Morris's whole book is about. This whole case is based on examples like this. All right. These are my favorites, the next two. That looks a little bit like a rabbit, maybe like a mouse. It's a bandicoot. Does anyone know what's kind of weird about a bandicoot? It's a marsupial. Here's the baby's running a pouch. This is my favorite marsupial. That's a thylacine. It's a Tasmanian wolf. It's extinct now, unfortunately. And not so much because it was selected by its environment for extinction, you know what I'm saying. Anyway, although you can argue, well, of course it was. That was anyway. It looks like a wolf. It probably acts like a wolf. I think it kind of eats like a wolf. And it's not a wolf. So this thing converged on this design, based presumably on its environment, not selection. But what it started from, somewhere different from a wolf. It's not a wolf. They converged on a design that looks wolfish. How to swim fast. Apologies to Michael Phelps. It's better to be shaped like a torpedo, to have sort of these interesting fins here and here. There's a dolphin, there's a tuna, and everyone knows these things do have a common ancestor, but it sure couldn't swim. And it didn't have fins, and it wasn't shaped like a torpedo. This is a mammal. That's a fish. I hope, and again, again, no one is sitting here saying, oh my gosh, well no, of course, but that's convergent evolution. How to fly, just grow some wings. These things have appeared repeatedly in evolution. They all look kind of similar. There's a blade, some muscles to move it. You know, these two wings here, a bat and a bird wing, those arose independently. What they have in common is the vertebrate forelimb, but not a wing. All right, there's an insect wing. This is my favorite. I scanned this right out of Conway Morris's book. Typical insect leg. There's a praying mantis. It's got an interesting leg. This thing is called a mantis paw. And boy, they sure look like they could be cousins. They arrived at these designs independently. That's convergent evolution. Under presumably very similar selective forces, convergent evolution. So what does all of this mean? Oh, by the way, I should remind you this. There's eyes convergently evolve. Eyes have apparently evolved repeatedly during the history of the world, although interestingly with some deep homology that they all sort of have in common. It's kind of something people are working on right now. Other examples. There's a whole chapter on smell in his book. He's got a great chapter called Shocking Convergence, referring to how different lineages have figured out how to make electricity and use it either to kill or mobilize prey or to use it to map the environment around them electrically. It's pretty cool stuff. Professor Blankensport will tell you all about that. And even multiple species have figured out that it's easy to deliver gametes into a target by taking a piece of tissue and pumping it full of blood. So I'll let your imagination go from there, but that's happened repeatedly in evolution. Nice example of convergence. Come up afterwards if you need a few more hints about what I'm talking about. What does all this mean? Here's what Conway Morris says. Evolution repeatedly arrives at similar solutions. There's areas of morphospace, and let's get our picture back up here, that almost seem like attractors, and that's a piece of jargon from an area of engineering that people might understand. So it's almost like evolution steers toward solutions to particular problems. And Conway Morris actually uses that term, attractors. Now, okay, adaptationists, and most famously guys like Richard Dawkins, Dan Dennett, his little twin, his philosopher, these guys would say, well, of course, it's all about adaptation, so of course everybody finds the same solution to the same problem. Duh! All right, so now, in fact, Dennett calls these things neat tricks. Look at evolution, see neat tricks. Evolution knows how to find them, it will find them. You want to, as he puts it, locomote through a transparent medium, you need eyes. You'll figure out a way to make eyes. Give me enough time, I'll give you an eye, and I don't care if you make me go back to start. I'll figure it out. So this is, adaptationists are all over this. They're like, yes, of course, convergence. They're on Conway Morris' side against Gould. They think it's idiotic to think that the story would turn out differently if you rewind the tape. But no, it'll be the same. Same planet, same story. Same, do they really mean that Matheson will appear right here, right now? No. But they do mean, do you think you'll eventually get a mammal-like thing? Yeah, they do. Okay, so, but Conway Morris addresses the point I wanted you to worry about, which is why, if Gould is right that the tree of life looks like this, situated like this in morphospace with white space, then Conway Morris wants you to ask, why is there white space? Okay, what that white space is areas of morphospace, right? Design space, you want to call it that? That's another phrase Dennett uses, that one, design space. That's unoccupied and apparently never been explored. Gould never really tells us what he thinks about that. I don't think he would disagree with what I'm about to say, but he doesn't think you need a reason for why this can get explored because, well, these guys never got there, that's why. Conway Morris says, no, I don't think so. Because whenever you put evolution into a space, it quickly finds the things that it needs. Quickly, whatever. It'll find eyes, and it'll do it over and over and over. And so, Conway Morris says, I'll tell you why this white space, that area is constrained, and evolution can't get there. And so this isn't nearly as interesting as you think, Steve, referring to Gould. You forgot to talk about the constraints in morphospace that make it so evolution can't get there. Carmen Morrison's is saying, and I know they're there, but he's saying, well, that could explain void space, couldn't it? Yeah. Do you understand why he's making that argument? He's saying, because guys, when we look at what evolution can do, it's really good. It doesn't miss a pitch. Some of you who've read both of these are wondering now if I'm setting up a